Good morning everyone, welcome to week number 2 where we are going to talk about the conduction heat transfer, or basically I am going to introduce you to the topic of conduction heat transfer. In the previous week we just had a very brief introduction starting from the fundamentals of thermodynamics or the laws of thermodynamics. I have tried to make you understand what are the needs of heat transfer, or where is the scope for heat transfer study. And there we have seen that while in thermodynamics we broadly focuses on the overall quantity of heat that gets transferred to or from the system. In case of heat transfer we focuses on the nature of that heat transfer, the mode of that heat transfer, and also we primarily tries to estimate the rate of heat transfer or the heat flux associated with any particular thermal energy transmission process. And there the idea of conduction, convection and radiation was introduced. We have also learned the basic laws for each of those heat transfers. Now, while the basic law for convection and radiation will also be used while studying conduction, but let us start with a bit more detailed about the conduction heat transfer, to be precise. Now, as we have discussed in the previous week, that in conduction heat transfer the nature of heat transmission or the primary mode of heat transmission comes from the molecular activity. Because of the random motion of the molecules in a gases, or because of the lattice vibration of the molecules in a solid, we have the energy transmission. Just to repeat on the same thing, like the situation is shown here for the gases. In the gases, you know that the volume of the domain available to us is extremely large compared to the volume occupied by the molecules. Accordingly, each of the molecules has significant amount of space, or significant distance can be covered by each molecule between two successive collisions. Accordingly, the molecules can keep on moving freely, and as they move, occasionally they collide with the neighboring molecules. Now, if there is any temperature gradient, say like the diagram shown here, if suppose this side we have a high temperature, let us call this T1, this side we have a low temperature, let us call this T2, and this T2 is less than T1, then the molecules, I probably have mentioned that in the previous lecture also, still I am repeating the same thing. The molecules which are close to this high temperature zone, they are expected to have higher energy content compared to the molecules which are close to this low temperature zone. Accordingly, the molecules in this zone will be having higher kinetic energy, because at the molecular level it is kinetic energy only is the form of energy that we need to consider. So, they will be moving randomly, or rather they will be moving with a higher kinetic energy compared to the second group of molecules. And if I draw one arbitrary plane somewhere here, then the number of molecules crossing this particular plane from top to bottom will be more compared to the number of molecules crossing it from bottom to top. Accordingly, there is a net energy transmission from the high temperature side to the low temperature side, and this particular thing we refer as the molecular diffusion. And also, when these high energy content molecules collide with a low energy content molecule, then they also transfer a larger amount of momentum to the low energy content molecule, and accordingly by molecular collision also the low energy level molecules can get can get some additional energy from the high energy level molecules. So, that is what we are referring as molecular collisions. So, molecular collisions and molecular diffusions are the two types of mechanism that we can have in a gas conduction. But generally the number of molecules being extremely small compared to the overall space available to us, the total conduction or capacity for a gas to transfer heat by conduction is generally extremely small compared to the convection or radiation mode of heat transmission. And also, if we think about the effect of temperature on this, as the temperature of the gas increases, their overall energy level increases, and accordingly their molecular activity also increases. So, you can expect the capacity for the gas to transmit energy by conduction or heat by conduction should keep on increasing with temperature. We shall be seeing that again shortly. Next, we talk about the liquids. In liquids also molecules are allowed to move freely, but not as freely as the gases. Rather, the molecules are generally bound together in somewhat close form clusters, and these clusters or a group of molecules generally float around with respect to each other. And therefore, both the mechanisms of molecular diffusion and molecular collisions are still valid, but as molecules are not allowed to move as freely as in case of gases. So, the effect of molecular collision may not be as much prominent compared to gases, but molecular diffusion is the primary mechanism of heat conduction in case of liquids, where the molecules can have bulk motion. Accordingly, as they move from high temperature zone to the low temperature zone, they carry energy with them as well. And then we can come to the solids. In case of solids, we know that solids are generally bound by a solid crystal structure or solid lattice structure, and therefore, the molecules are not allowed to move at all, or at least not allowed to move just similar to the gas or liquid molecules, but of course, they can move while maintaining their own position. That means, they can vibrate with respect to their base position, and that lattice vibration is the primary mode of heat conduction in case of solids. Like the high, as I probably had mentioned again, say if this is one molecule which is at a higher energy level and this is molecule number 2 which is at a lower energy level, then we can expect that molecule number 1, both the molecules will be vibrating, but the vibration amplitude for molecule number 1 is expected to be larger than the vibration amplitude for molecule number 2. And as they are vibrating and in lattice structure, as they are quite close to each other, so during vibration this molecule number 1 will also try to induce the same amount of vibration amplitude to molecule number 2, and accordingly it will transmit some amount of energy to this molecule number 2, and this lattice vibration is the primary mode of mechanism. There is a secondary mode of mechanism that is applicable particularly for conducting solids, the flow of free electrons. In a conductor, there are lots of free electrons available, and as they keep on moving from one position to another position, maybe because of some kind of potential difference, they will also lead to the transmission of conduction energy or thermal energy. So, in case of solid, while in case of gases and liquids, we have primary mechanism as molecular diffusion and also molecular collision, most prevalent in case of gases. In fact, gases and solids together we can also refer them as fluid. So, while in case of fluids, we have molecular diffusion and molecular collisions as the primary mechanism behind conduction heat transfer. In case of solid, we have lattice vibration and the flow of free electrons in case of conducting solids as the primary mechanisms. Next is the Fourier's law of heat conduction, which I have already introduced, but I am now trying to go into a bit more detail on that. Here I am showing you one block. Just assume it is a block of some thickness delta x, and its dimensions in the other two directions are extremely small. Let us apply a coordinate system somewhat like this. Say this is our x direction, this is our y direction, and this is the z direction. Now, we are assuming that the dimension for this particular solid in the y and z direction is infinite, or practically speaking you can say that the dimensions in the y and z directions are extremely large compared to this delta x, and then it becomes very much a one dimensional kind of scenario. Why one dimension? That I shall be coming in the next class, but for the moment you just consider that we have a block where we have temperature T1 at one end and temperature T2 at the other end. Here this T2 is less than T1, and the distance between these two planes is delta x. So, as the and A refers to the area of the plate, that is the area of the YZ surface. So, it is a situation of pure conduction, because inside the domain inside this, the space inside these two plates has been filled by a solid, and as there is no fluid flow available, then we have it as only conduction, there is no convection, and also we are neglecting any kind of radiation mode also. Again, as I have mentioned in the previous week, that convection and radiation are primarily related to the surface of a solid, whereas here we are talking about transfer inside the surface. So, conduction is the mode of heat transfer. In this kind of scenario, it has been observed that if suppose capital Q dot refers to the total rate of heat transmission by conduction, it has been found that that is proportional to the temperature difference delta T, which is nothing but T1 minus T2 in this case. It is also proportional to the area of the plates, but it has been found to be inversely proportional to the delta x. All these three observations are purely from experiments or observation. The Fourier's law of heat conduction, which we are trying to frame here, has not come from any kind of mathematical background, rather it is a purely phenomenological law which has been observed just from experiments, like say the laws of thermodynamics as well. These are all phenomenological law. So, if we combine these three together now, then what we can write? The rate of heat transmission then is proportional to T1 minus T2 upon delta x into the area of the plate, or if we introduce a proportionality constant, then we can write this as k into delta T upon delta x into area, where this k is the constant of proportionality. Now, if the thickness of the plate is extremely small, that is if delta x tends to 0, then how we can modify this? Then this expression becomes, okay, here I should have the equal to sign. Okay. So, q dot in that limiting case is limit of delta x tends to 0, k delta T upon delta x into A becomes equal to minus k into dt dx into area, and I am putting a negative sign here. So, this dt dx basically refers to the temperature gradient, because we know that limit delta x tends to 0, delta T upon delta x can be represented by this, and I am putting the negative sign because as we are moving in the positive x direction, temperature is reducing, like shown by this particular profile, temperature is continuously reducing. So, dt dx actually is a negative quantity, and therefore, to make this heat transfer positive or rate of heat transmission positive, we are putting this negative sign. So, the one dimensional form of Fourier's law of heat conduction then comes as q dot is equal to minus k A into dt dx, and I should put the suffix x here to indicate that here we are talking about heat transmission in the x direction only, or if I divide this by the area, then we get the heat flux in the x direction to be equal to minus k of dt dx. This is the equation that I wrote in the last class as well, but we have as such not used this any so far. So, this is the form of the Fourier's law of heat conduction in x direction. However, one thing we have to understand, or couple of things I would like to mention here, this particular heat flux quantity, can you tell me it is a scalar or a vector? Whether you know from your basic definitions from physics that scalar refers to a quantity which has only magnitude but no directions, whereas vector has both magnitude and directions. Now, your entire study of thermodynamics, you never bothered about any quantity being scalar or vector, because thermodynamics never talks about any rate or directions as such. Of course, in second law we get a direction of heat transfer from high temperature to low temperature, but that does not talk about the direction in terms of space coordinates. But here we are talking about proper directions, and therefore, whether it is scalar or vector, it is important to know. Like the temperature is a scalar quantity, this k that I am talking about, that can also be taken as a scalar quantity for the moment, but this heat flux is a vector quantity, because here we are talking about the heat flux in a particular direction. And what is the direction? The direction is perpendicular, like shown here, perpendicular to the area A that we are talking about. So, the expression that we have got here from Fourier's law of heat conduction, here you are getting the mathematical expression for the heat flux in the x direction, or you can say it is we are getting the expression for heat flux acting normal to this area A. Here the area A we have taken on the yz plane, that is perpendicular to the x direction, but it is very much possible that the area may have a 3-dimensional orientation as well, something hypothetical area that we can draw something like this, which has its normal, like if say this is the normal of this normal can have all 3 coordinate directions, and in that case there is a more generalized form of Fourier's law of heat conduction, where we write that the q dot x is equal to minus k into area into grad of T, but this grad is a vector operator, or we can write the heat flux to be equal to minus k grad of T, where this grad of T refers to dou T dou x in the x direction plus dou t dou I in the y direction plus dou t dou z in the z direction, with I j k being the corresponding unit vectors. So, we can then write that the generalized form of Fourier's law of heat conduction, quite often we put a subscript in to indicate that here talking about heat transfer in this particular normal direction normal to the area, is equal to minus k grad T, that is we can write this to be equal to minus k into dou t dou x of I plus dou t dou I of j plus dou t dou z of k, or maybe just in terms of operator dou dou x of I plus dou dou y of j dou dou z of k acting over this t. And sometimes just to indicate the direction of in, as everything comes from the direction of in, then we sometimes also write this one as minus k into dou t dou n in the nth direction, but this dou t dou n is the representative of this distribution. This is dou dou n cap operator just represents this dou dou x of I plus dou dou y of j plus dou dou z of k. Here this n is the normal to the area that we are talking about, and so this particular representation is directly giving you the value of heat flux in the nth direction. There is another way we can write this, q dot double prime in the nth direction into the orientation, because here you are talking about the vector quantity, whereas in this expression this is the just magnitude of the heat flux in the nth direction, and n cap is the orientation of the surface. So, this heat flux being a vector quantity, we can easily classify or rather separate this one into 3 components as well. So, we can easily write this q dot double prime n as its x component acting in along the I direction plus its y component acting along the z direction and its z component acting along the z direction, where this x component is given as minus k x, the temperature gradient in the x direction, the y component is given as minus k y into temperature gradient in the y direction, and the z component is given as minus k z into the temperature variation in the or temperature gradient in the z direction. So, this is a more complete representation of the Fourier's law of heat conduction. Here k x, k y and k z are the proportionality constants which may have some direction dependent nature in certain materials. Thankfully, for most of the materials k x, k y and k z all are equal to each other, and we call this kind of materials to be isotropic materials. So, for isotropic materials we have k x is equal to k y is equal to k z, let us say equal to some k, and therefore, for isotropic materials we can easily write this to be equal to the heat flux in the nth direction to be equal to minus of k into dou t dou n to n cap, just this form that we have written, but actually in this form we have assumed k to the material to be isotropic, but in more proper sense k should be a part of the derivation that I have mentioned here. And in certain cases k for most of the materials, as I have mentioned, most of the materials are isotropic in nature, but certain materials we may have to consider this variation. So, this is the scenario that I am talking about. This is of course drawn in a 2-dimensional plane. Now, what else we can say about the surface? Here we are talking about heat transfer in the direction normal to the area that we are talking about. Then what is the temperature along the area? Here heat is being transferred normal to the area, and we can of course get components in x, y or z directions, but what about the component along the surface? The tangential component of course has to be 0, and what does that mean? The tangential component of heat flux along this particular surface is 0, and that is possible only when the temperature along this surface is equal throughout. That means the surface that we are talking about is an isotherm or a constant temperature surface. So, in Fourier's law, basically we are getting the expression for heat flux in the direction normal to an isotherm, and that is given by for the last time I write the expression, the heat flux in the direction normal to an isotherm is expressed as minus k grad T in the normal direction, or maybe just grad T, where the grad itself will take care of the direction part. Now, the K that I have mentioned about, it is known as the thermal conductivity, and it is a very important property of material, because it is the property which dominates the entire phenomenon of heat conduction. So, if I just go back to the basic representations, there we have found that the transmission in the x direction is was given as minus k x dou t dou x, it was minus k y dou t dou y, and this was minus k z dou t dou z. So, from there we can write k x is equal to minus of the heat flux in the x direction divided by the corresponding temperature gradient. Similarly, k y will be equal to the heat flux in the y direction divided by corresponding temperature gradient, and k z will be equal to the heat flux in the z direction divided by corresponding temperature gradient. Again, as I have mentioned, for isotropic materials all three are equal to each other, but the important thing here is that the magnitude of heat transfer, like if we talk about any one of them, let us say pick up the heat flux in the x direction, here the magnitude is dependent not only on the temperature gradient, but on the k it's also, like the situation shown here. Here I am showing you the situation of two different materials. We have two blocks of identical dimension, both of them are having thickness of 1 meter. For both blocks, the temperature of the left face is 30 degree Celsius and on the right face it is 20 degree Celsius. So, the temperature gradient that is acting, assuming one dimensional heat conduction here, then effective temperature gradient, that is the dt dx, assuming this direction to be x, dt dx can be approximated as delta T upon delta x. In this case, then it is equal to 10 Kelvin, 10 degree Celsius or 10 Kelvin divided by 1 meter, that is 10 Kelvin per meter. Here this capital K is important, capital K denotes Kelvin, whereas if we write small k, that refers to the kilo prefix. So, the effective temperature gradient is equal for both the cases. However, in one case we have a material of copper which has a thermal conductivity of this, and this case we have silicon which has a thermal conductivity of this. Then what will be the corresponding rate of heat transfer? So, the heat flux in the x direction for the first material will be equal to its thermal conductivity, that is 401 into the effective temperature gradient, that is 4010 watt per meter square. In the previous week we have discussed about the units, so I am sure that is clear to you. Similarly, the heat conduction heat flux in the x direction for the second situation, here thermal conductivity is 148 into the effective temperature gradient. So, it is 1480. Accordingly, different materials can show different rate of heat transfer despite being subjected to the same temperature gradient, just depending upon the value of its thermal conductivity. Some of the materials like copper, aluminum, etc. are extremely good conductors. Generally, the materials which are good electrical conductors, solid materials, that is, they are also good thermal conductors, because they have lots of free electrons, and the free electrons contribute towards the transmission of both electricity and thermal energy, whereas certain materials can have extremely low thermal conductivity as well. If we just visualize the normal chart of thermal conductivity for different materials. For gases, generally the thermal conductivity level is very low, just shown here. For liquids, we are more on this side. Water, mercury is one of the conducting metals which remains in liquid state. So, its conductivity is significantly higher. Look at the level, for mercury it is of the order of 10 watt per meter Kelvin, whereas for gases of hydrogen etc., it is just 0.1. So, that is 2 order difference. When you go to something like aluminum or silver, that is 1000. So, that is or not 1000 actually silver, but silver will be in the range of copper only. So, that is extremely high conductivity that we are talking about. Now, if we are talking about the source or reason behind conductivity, generally as we have seen, particularly for solids, there are two ways conduction or heat can get transmitted by conduction. One is the lattice vibration, other is the molecular activity. Accordingly, conductivity also can have two components. So, the thermal conductivity for solids, that is, so if I write say K solid, can generally have two parts, one part corresponding to the lattice vibration and another part coming from the electronic activity. And the first part refers to the lattice vibration, second part corresponds to the electrical activity. Now, from the kinetic theory, it generally can be written as the value of K for any solids is equal to 1 by 3 into capital C into C bar into lambda MFP, that is the mean free path. Here the quantity C bar refers to, like when you are talking about a conducting material, here this capital C refers to the electron specific heat, per unit volume. C bar refers to the mean electron velocity, where lambda MPH refers to the mean free path of the electron. So, you know the idea of mean free path. Mean free path refers to the average distance travelled by each electron, in this case between two successive collisions. So, when you are talking about a conductor, this is basically the expression that I have written that corresponds to the electrical part. So, once we know these quantities from following kinetic theory, you can get some idea about this K electron. Now, when you are talking about a conductor, the electron velocity is quite high, the mean free path is also high, and accordingly we get this component to be extremely high. However, for non-conductors, this component can be quite low, then the lattice part becomes more significant. Certain non-conductors like say diamonds, which are electrically non-conductor, or beryllium, for them this part is more significant. If we want to calculate the K lattice, then we can use the same relation following kinetic theory, but instead of electron we are going to have phonons in this case. So, capital C becomes phonon specific heat per unit volume, C bar becomes mean phonon velocity, and lambda MPH refers to the mean free path of the phonons. So, for different materials we can have different values for this, but in general for conductors the K electron is extremely large, K lattice is almost negligible for materials like copper, silver or electrons, whereas for non-conductors the lattice part is more important. So, for non-conducting solids particularly, if they are arranged in certain structure, then the value of K lattice also will be quite high. So, amorphous materials has this K lattice value to be quite small compared to the crystalline materials, like I have given the example of diamond. Another excellent example can be graphite. You know that in case of graphite the carbon molecules are arranged in certain layers. So, if we think about conductivity along a layer, then that will be very high because we have particular lattice structure, whereas if we are going from one layer to another layer, then the conductivity is quite low because in between there is there is no lattice structure, the layers are more or less floating over it to be placed in a very crude way. So, this is the chart that I have given, and these are the values for thermal conductivity, some of the common materials under normal temperature, solid, liquid and gas, for all of them it is given. Look at the values. For silver it is in the range of 429, copper 401, gold and aluminum 237. So aluminum and copper are two very common materials that are used in the cases where you want high conduction. Silver is also used in precise electrical instruments and also in certain thermal instruments. But look at the other thing, diamond, it is having an extremely large value of this thermal conductivity, and that is because of its crystalline structure. This entire value of this 2300, or almost entire part of this one, is coming only from the k lattice part, because this is a non-conductor. So, k electron is 0, whereas for these materials k electron is the one that is prevalent for this. You can say the same almost for mercury and iron as well. They are metallic, and while mercury is liquid. So, for them the molecular diffusion also plays a role, but still mercury being a metal, it has certain amount of free electrons which also contributes to its high conductivity. Of course, not as high compared to copper or aluminum, but still high than several other materials. Stainless steel, which we commonly use as utensils etc., will be having a value in the range of 13 to 15. There are different grades of stainless steel, depending on the grade the value varies, but generally in the range of 13 to 15. Now, look at certain other materials, the brick, something like this, wood 0.17, rubber 0.13 and glass fiber 0.043, glass wool or foam 0.026. These values are extremely small, and as these materials are having extremely small thermal conductivity, so they are actually used as insulators. Insulator is the opposite of conductors, or the objective of insulators is to reduce the thermal conduction. So, for insulators we want low thermal conductivity. And the materials which I have encircled here, they all can be very good thermal insulators, like wood or this glass fiber or rigid foams. They are very commonly used. Foams are also used for suppression of fire because of its low thermal conductivity. Now, if you move to some other materials, like for water, liquid water, that is in the range of 0.6. So, water is also a poor thermal conductor, but much better than something like glass wool etc., at least one order difference. And this is interesting, human skin 0.37. So, our skin is also not a very good conductor, and that actually helps us when we are exposed to very high or very low temperatures. Like when you are exposed to very high temperature, skin will act something like an insulator, and it will not allow the heat to pass through very quickly. Whereas when you are exposed to very low temperature, again the skin will allow us to retain our body heat for longer period compared to any material having higher conductivity. Also, the dresses that we wear, we want the conductivity to be low, so that we can retain the body heat, particularly in cold environment. Like the cold environment, we go for woolens. Now, wool has lower thermal conductivity compared to cottons or polyester materials, and therefore, it is able to restrict the leakage of heat from the body to the surrounding by conduction. Now, this is a chart which shows the temperature dependence of thermal conductivity for solids. As the temperature increases, the electronic movement part, that does not get affected that much, but lattice structure, the k lattice part generally keeps on reducing. Accordingly, you can see there is a little bit of reduction for most of the materials. The thermal conductivity reduces a bit, but exception can be platinum at high temperature or certain kinds of quartz. If you go to liquids now, for liquids, of course, we have molecular diffusion as the primary mechanism, and that is why for liquids generally as the temperature increases, their conductivity reduces, like ammonia or refrigerants you can see. For water, it generally increases a bit, and then at once you go to higher temperature, it keeps on reducing because water has gone to the vapor phase. That glycerin or certain degrees of engine oil can be exceptions, so thermal conductivity can increase a bit. For gases then, As I mentioned, as the temperature increases, the molecular activity increases. For gases, the source of conduction heat transfer is molecular diffusion and also molecular collision. Now, as temperature increases, the level of both molecular collision and molecular diffusion keeps on increasing. Accordingly, their thermal conductivity also keeps on increasing, just shown here. Like for as the temperature changes from something around 150 Kelvin to 600 Kelvin, thermal conductivity of hydrogen, you can see it has gone from 0.1 to about 0.3. So, there is 200% increase in the value of thermal conductivity for hydrogen. For gases, if we want to calculate this, quite often we follow a relation again from the kinetic theory. I am just writing it from the source, you do not have to remember this relation, this is more to give you an idea on how to estimate the thermal conductivity for gases from kinetic theory. It is about 1/3 of specific heat at constant volume into rho C bar into lambda MPH. Here C bar and lambda MPH are just the definition that we used in the previous slides. Rho is the density, CV is the specific heat at constant volume, and the lambda MPH for ideal gases can generally be expressed as Kb into T divided by root 2 pi d square rho, where Kb is the Boltzmann constant, whose value definitely you know, which is 1.38 into 10 minus 23 joule per Kelvin, and d is the average diameter of the gas molecules or statistically estimated diameter of the gas molecules, and rho is the density, T is the absolute temperature. So, once we know the temperature of a specific gas, probably we can estimate density, particularly if we know the temperature and pressure, we can calculate its density using ideal gas equation of state. Also, we can get some idea about the value of its diameter, which generally is related to the molecular weight. And then once we know the lambda MPH, then we can calculate the thermal conductivity as well. So, this is about thermal conductivity. There is another property that is also very important, that is called the thermal diffusivity. Now, the thermophysical properties for any matter are generally classified into two categories. So, thermophysical properties can be classified as one group which we call the thermodynamic properties, and other is the transport properties. Thermodynamic properties refer to properties like examples can be density, specific heat, which are used extensively in thermodynamic analysis, because they are used more for relating the gross behavior of a system, and they are primarily associated with the equilibrium state of the system. When the system reaches equilibrium, we can easily calculate the value of these quantities, and accordingly we call them thermodynamic quantities. But transport quantities are associated with the transport of certain parameter, transport or movement or certain parameter crossing the boundary of a system, then the transport properties comes into picture. Already couple of transport properties you must be knowing. One transport property is viscosity or dynamic viscosity, which you are introduced in your fluid mechanics. Generally the symbol mu is used for this. Dynamic viscosity is associated with the transport of what? It is associated with the transport of momentum. Another example that just we have discussed, that is the thermal conductivity. We are using K, but in certain literature you may see the symbol lambda also, which is associated with the diffusion of thermal energy or transport of thermal energy. Another quite popular transport property is the mass diffusivity. Generally the symbol capital D is reserved for this, which is associated with mass transfer. So, this way we can have several kind of transport properties. If the electrical materials or something like electron is getting transported, accordingly we can also define more transport properties. So, thermal conductivity is a transport property quite similar to the dynamic viscosity, whereas rho and Cp or Cv, these are thermodynamic properties. Now, this product rho into Cp is generally known as the volumetric heat capacity. Why we are giving such a name? What is rho? Mass per unit volume. So, rho into Cp is the total capacity of the capacity of the material or constant substance to store energy per unit volume, and that is why we are calling it volumetric heat capacity. Of course, rho and Cp can vary widely for different materials, but quite often this product rho Cp product can be of the same order. Now, when we are dealing with a certain rho Cp, certain substance whose rho Cp value is quite high, say in the grid, it is of the order of say 1. Okay, what should be the unit of this rho Cp product? Rho as a unit of, let me write in the vacant space. So, you know rho has the unit of kg per meter cube, and what is the unit of Cp? Cp is joule per kg Kelvin. So, its unit becomes then joule per meter cube Kelvin, its capacity to store energy. Now, when the rho Cp value is greater than 1 megajoule per meter cube Kelvin, that is greater than 10 to the power 6 megajoule per meter cube Kelvin, this kind of materials are used for energy storage. Whereas, when this rho Cp is quite low, say in the order of 1 kilojoule per meter cube Kelvin, then this kind of materials can't be used, they are not suitable for thermal energy storage as well. What is the value of rho Cp for liquid water? Can you guess? For water under atmospheric condition, that is, we have rho approximately equal to 1000 kg per meter cube, and what is Cp for water? It is about 4.18 kilojoule per kg Kelvin. So, rho Cp product for water will be equal to 4.18 into 10 to the power 3 into 10 to the power 3 for density, that is 4.18 into 10 to the power 6, or at least of that order of joule per kg Kelvin. So, it is greater than 1 megajoule meter cube Kelvin, should have been. It is greater than 1 megajoule per meter cube Kelvin. So, water can also be a good material for energy storage. You must have seen at our houses also, like once we heat water to a certain temperature, to a higher temperature, then it takes long time for the water to dissipate the heat and come back to the lower temperatures. But now, the ratio of one transport property, which is the thermal conductivity, and product of two thermodynamic properties, which is this rho Cp, the volumetric heat capacity, is known as the thermal diffusivity. It is alpha. Generally, the symbol alpha is reserved for this. K is the thermal conductivity in the numerator, and this volumetric heat capacity in the denominator, which we are calling the thermal diffusivity. It gives us an idea about the ability of a material to transmit energy compared to its ability to store, because in the numerator you have thermal conductivity, which characterizes the ability of the material to transport energy by conduction. In the denominator we have this rho Cp product, which determines the ability for this material to store thermal energy. Accordingly, this gives us a ratio of ability of the material to transmit energy compared to its capacity to store. So, if we are talking about two materials having different values of alpha, then the one having higher value of alpha is expected to transmit energy more. Like in your school level physics, you have probably heard about this experiment. Say we are having a surface which is maintained at a certain high temperature, and then we are having two rods of different material. They are having identical dimension, both of them are exposed to the surrounding, or at least the tip is exposed to the surrounding. These surfaces may be insulated, only the tip is exposed to the surrounding, which is a temperature much lower than the surface. Now, their dimensions are also identical and they are exposed to the same temperature difference. Then the time it requires for the temperature or for this end to attain the temperature of the base, or then that will depend upon the value of the alpha, for which case the time will be larger. Just think, this is something that I will ask again in the next lecture. But what will be the unit for this thermal diffusivity? K is the thermal conductivity in the numerator, which we have identified as a unit of watt, that is joule second per meter Kelvin, and in the denominator we have the volumetric heat capacity, which has a unit of joule per meter cube Kelvin. So, joule and Kelvin cancels out. So, we are left with then meter square per second. We have left with meter square per second. Have you seen this unit earlier? Do you remember nu, the kinematic viscosity, which is defined as the ratio of dynamic viscosity and density, that is also having an unit of meter square per second, because this alpha and this nu, they are analogous to each other. The alpha characterizes the thermal diffusion, whereas this one characterizes the momentum diffusion, and that is why they are very much analogous to each other. So, once we know the value of these properties, we can easily calculate the value of alpha. Let us take some examples. Let us say I have data for aluminum, pure aluminum, that is for pure aluminum rho is given as 2702 kg per meter cube, its specific heat is equal to 903 joule per kg Kelvin. Remember, aluminum, we are talking about solid materials, so Cp and Cv are identical for them, and thermal conductivity K for aluminum we have seen in the previous slide, 237 watt per meter Kelvin. So, if you combine them, then alpha will be equal to, all are expressed in basic SI units. So, we do not have to talk about the unit conversion. So, we have rho into Cp. So, accordingly the value of alpha is coming to be an extremely small one, 97.1 into 10 to the power minus 6 meter square per second. So, the value of our alpha for aluminum is extremely small, whereas if we talk about the same values of aluminum at say higher temperatures. Now, initial values I have given at 300 degree Celsius. Now, I have the data at 300 Kelvin, that is 27 degree Celsius. Now, I have the data at 700 Kelvin. For 700 Kelvin, I am changing these numbers. It has been found to be the density remains more or less the same, 2702. Specific heat changes, it increases to 1090, and thermal conductivity, we know that solids, we have seen thermal conductivity solid decreases a bit with temperature. So, if we put these numbers, then we have 225 in the numerator, 2702 remains and 1090. Accordingly, its thermal diffusivity reduces even more, it comes to be something like approximately 76 into 10 to the minus 6 meter square per second. So, this is purely dependent on the materials, and also with temperature, as the property changes, the value of thermal diffusivity also changes, accordingly modifying the capacity of the material to transmit heat by conduction. So, in today's class we have been introduced to two different thermophysical properties, transport properties, that is, and in the next class we shall be talking about using the Fourier's law of heat conduction for development of the heat diffusion equation. So, just to summarize our discussion today, we discussed briefly the mechanism of conduction heat transfer, then the generalized form of Fourier's law of heat conduction in 3-dimensional form in terms of the generalized temperature gradient or acting in the direction normal to an isothermal surface, that we have discussed. Then we discussed in detail about the thermal conductivity, its contribution coming from the lattice structure and also from the free electrons, particularly in case of solids, and then the concept of thermal diffusivity was introduced, which is a ratio of thermal conductivity to the volumetric heat capacity, and accordingly it gives an idea about the relative importance or relative significance of thermal conduction to the thermal energy storage. So, that is where I would like to stop today. In the next class, as I have mentioned, I shall be developing the generalized version of the heat diffusion equation for in a solid medium to start with. Till then you please revise this lecture, and once you are confident about this, then only please move to the next video. Thank you very much.